This is an introduction to fluorescence spectroscopy. Fluorescence is a technique that uses light as a source for excitation of the analyte and detects emission of light from the analyte at a longer wavelength. In this particular slide, fluorescence is illustrated for two analytes, quinine and fluorescein. And as we can appreciate, quinine has a blue fluorescence that results from excitation with a shorter wavelength from a violet laser. Similarly, the fluorescence from fluorescein is yellowish greenish in nature, corresponding to the excitation of this analyte by the same laser, the violet light from this laser. To understand the origin of the excitation and emission spectra, it's important to look at energy diagrams. For example, the energy diagram of a molecule is illustrated here for the absorption process. We have the ground state, we have the excited state of a singlet excited state in this particular case. The absorption process is illustrated by a line that goes from the ground state to the excited state. And we can see that that excited state also has several lines representing different energy levels caused by different vibrational states. This process of absorption is extremely fast. It happens in the order of femtoseconds. A femtosecond is 10 to the minus 15 seconds. And once light is absorbed, there is another process called vibrational relaxation that happens very quickly as well in the order of 10 to the minus 12 seconds or a picosecond, that brings basically all the potential states to the lowest vibrational state possible, represented by this thick dark line. At that point in time, the molecule could be experiencing an internal conversion, which is basically transition to another excited state that also has vibrational states, in which relaxation could happen again to go to the lowest vibrational state. The second component of the energy diagram is that leads to fluorescence or emission of light. So once a molecule is at the lowest vibrational state, there is a possible process in which there is going to be a transition from that lowest vibrational state in the excited state down to the ground state. It is important to observe that doesn't happen to the lowest vibrational state. It could happen to any of these levels that illustrate different vibrational states. That means that there is going to be a slightly different energy for each of these possible transitions. Slightly different energies of the emission of light correspond to different wavelengths that will correspond to a profile such as the one that we observed in the emission profile. That is, in the previous diagram or the previous slide, the fluorescence profile or emission profile we observed corresponds to the process of fluorescence that we have over here. A third component of an energy diagram are those that correspond to processes that are not necessarily convenient for the analysis by fluorescence. Those are competitive processes, such as, for instance, transitioning to another electronic state, such as that is based on intersystem crossing, that may lead to other things like phosphorescence, or also may result in the loss of the energy in the excited state through internal and external conversion that results in generation of heat in the sample. And lastly, it is possible that in some cases the molecule just basically experiences photodissociation or dissociation. So to appreciate the importance of these processes to fluorescence, one considers the property called quantum yield. Quantum yield is an indication of how fast or how frequent fluorescence occurs, represented by the rate of fluorescence, versus the rate at which other processes occur in an excited state. So here we have representation of how fast these processes occur, and this includes fluorescence, intersystem crossing, external conversion, internal conversion, pre-dissociation, and dissociation. For instance, if each photon that we used or is absorbed in a system is converted into a fluorescence photon, the quantum yield will be equal to 1. That is, Kf over Kf, and the other ones are not present, will be equal to 1. However, if we have systems in which the other processes are prevalent, the quantum yield will be much less than 1. In general, for analytical purposes, quantum yield must be as high as possible. Closer to 1 is better than closer to 0. Here we have examples of analytes that can be analyzed by fluorescence spectroscopy and analytes that cannot be analyzed by fluorescence spectroscopy. Those that have a low quantum yield, close to 0, are deemed non-fluorescent and usually cannot be analyzed by fluorescence spectroscopy. Here we have pyridine, furan, pyrrole, and thiophene, and as we can see, their structures are relatively simple. On the other hand, molecules like quinoline that have a conjugated system of pi electrons tend to be fluorescent, and this particular analyte is characterized by a much higher quantum yield than 0. So in general then, any analyte that has a quantum yield greater than 0 could be potentially analyzed by fluorescence spectroscopy. The instrumentation to measure fluorescence properties consists of two types. First, we'll discuss something that is called a spectrofluorometer. And spectrofluorometer is an instrument that will allow us to obtain excitation and emission spectra, and at the same time will allow us to do measurements of fluorescence intensity. One of the practices in understanding what an instrument is like and do is identifying first where the sample is located. Here we have the sample compartment. Second, we can identify the source of light. In this case, we have a xenon lamp. Third, we can identify where the light will be detected, that is the fluorescence light, right at the sample photomultiplier tube. Lastly, we need to understand how we're going to distinguish between excitation and emission light. And for that, we are going to be using monochromators. Monochromators are instrument components in which light can be dispersed, in this case by a grating, and selected by wavelength through a slit. And by doing that, we could potentially illuminate the sample just with a wavelength of interest so that we can excite the sample. Second, once fluorescence is emitted, we can select the fluorescence emission with a second monochromator that will allow us to transmit the light or fluorescence of interest towards the detector. The spectrofluorometer could be used in two modes. In the first mode, can help us obtain an emission spectrum. Here, the trick consists of fixing the wavelength selector so that we can actually excite the sample only with one single wavelength or a very narrow wavelength region, and then vary the wavelength selector for the emission. This will lead to the formation or the measurement of an emission spectrum. The other way is by obtaining an excitation spectrum. Here, we reverse the relative use of the monochromators. We can fix the wavelength of a selector for emission, that is the one that will collect the fluorescence or select the fluorescence, and we will vary the wavelength selector for excitation, leading to the acquisition of excitation spectrum. Another way to measure fluorescence is use of an instrument called a fluorometer. The key difference here is that both the excitation and emission wavelengths are fixed, and that is accomplished by replacing the monochromators with an excitation filter, which normally indicates the wavelengths of maximum transmission, and a range width, indicating how wide in nanometers that particular range is. For instance, this will indicate that we are exciting a sample at 488 nanometers and that the range of excitation is 20 nanometers wide. That is from 478 to 498 nanometers. Similarly, to collect fluorescence, we use an emission filter that again follows another filter, and as we recall before, the wavelength of emission is longer than the wavelength of excitation, which makes sense with the type of filter that were selected, the 520 DF20 versus the 488 DF20. Regardless whether we are using a spectrofluorometer or a fluorometer, we can use both instrumentations for analytical purposes. To appreciate the quantitative power of fluorescence spectroscopy, we need to look at the figures of merit. So fluorescence spectroscopy is highly quantitative. That is, we can change the concentration of the analyte, say quinine or fluorescein, and as we increase the concentration of these analytes, we will increase the fluorescence response. The technique is also highly sensitive, meaning that each molecule of quinine or fluorescein could be excited many times by photons that are absorbed and generates hundreds of photons from a single molecule. The technique also has low background because if we recall from a previous slide, the orientation that we have for excitation and emission of a sample is at 90 degrees. And in addition to that, we have the monochromators that allows us to selectively monitor or select the wavelengths of excitation and emission. Combining those two factors, the high sensitivity and the low background, leads to detection of molecules in very low amounts. Fluorescence spectroscopy is one of the championing techniques in terms of being able to detect single molecules, and this is thanks to the high sensitivity and low background of this particular technique. For more information on this technique, see the textbook Skog, Holler and Crouch, Principles of Instrumental Analysis, 6th edition.